This video, I will discuss Radix-2 decimation in time fast Fourier transform algorithm or DIT-FFT algorithm. DIT stands for decimation in time, FFT stands for fast Fourier transform algorithm. So DIT-FFT algorithm uses divide and conquer approach. Let me show you the block diagram of DIT-FFT algorithm. Later we will discuss about DIT-FFT algorithm. So this is the block diagram of DIT-FFT algorithm. Here we can see that there is a n point DFT. Here we have n by 2 point DFT, and another block we have n by 2 point DFT, and here we have n by 4 point DFT, and so on. In DIT-FFT algorithm, as I said, it uses divide and conquer approach. The n point DFT is divided into two n by 2 point DFTs, and each n by 2 point DFT again divided into n by 4 point DFTs, and so on until it reaches 2 point DFT. This is the basic concept of DIT-FFT algorithm. Now let's see how to divide this n point DFT into 2n by 2 point DFT. That is known as first stage decimation. That is, so this is n point DFT. I am considering n is equal to 8, so it is n point 8 point DFT. So dividing 8 point DFT into two 4 point DFTs is known as first stage decimation. Then dividing this into n by 4 point DFT is known as second point or second stage decimation. So first we'll start with the first stage decimation, that is 8 point DFT is divided into 2n by 2 point DFTs. We have 8 inputs and here we have 8 outputs. So here these are the inputs. So these are the inputs, and here these are the outputs. So we'll assume that x of n are the inputs and x of k, that is DFT, are the outputs. Assume that x of n is n point sequence. It means that x of n consists of n number of samples, where n is, say, integer power of 2. That is, I can say n is equal to 2 power r, where r is integer. R is integer. Now for understanding purpose, I will consider n is equal to 8. In that case, I can represent x of n as x of n is equal to, it consists of 8 samples, that is x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6, and x of 7. So now the x of n sequence is decimated into 2n by 2 sequence. Now let the sequence x of n is decimated into 2n by 2 point sequences as, say, f1 of n and f2 of n. That is, x of n is divided into 2n by 2 point DFTs, f1 of n and f2 of n. We'll assume that f1 of n contains even numbered samples. Even numbered samples of x of n, and let f2 of n contains contains odd numbered samples of x of n. That is here. So here I have assumed that x of n consists of 8 samples. So f1 of n consists of even numbered samples. So even numbered samples are x of 0, x of 2, x of 4 and x of 6. So similarly the odd number samples are x of 1, x of 3, x of 5 and x of 7. So now in general I can write f1 of n and f2 of n in terms of x of n as f1 of n is nothing but x of 2n, where n varies from 0, 1, 2 up to n by 2 minus 1, because f1 of n is n by 2 point DFT. Similarly, f2 of n contains odd samples, so we are supposed to write it as 2n plus 1, where n varies from 0, 1, 2 up to n by 2 minus 1, because f2 of n is also n by 2 point DFT. So now we know that DFT of any sequence x of n is given by x of k is equal to summation n is equal to 0 to n minus 1 x of n twiddle factor wn power nk, where k varies from 0 to n minus 1. We'll call it as equation 1. This now I will try to represent x of equation number 1 in terms of even and odd sequences. So now considering even and odd samples, equation 1 can be written as, that is, x of k is equal to summation n equal to 0 to n by 2 minus 1 x of n. I will consider this as even wn power nk plus summation odd samples I will take here n by 2 minus 1 x of n wn power nk. Therefore I can represent it as summation, so n is equal to 0 to n by 2 minus 1. So even samples we have represented as x of 2n wn power n is replaced by 2n into k, plus here this summation consists of odd samples n by 2 minus 1 x of, so odd samples here we have written x of 2n plus 1, that is x of 2n plus 1 into wn power n is replaced by 2n plus 1 into k. Further I can represent this expression as x of k is equal to summation n is equal to 0 to n by 2 minus 1 x of 2n is nothing but f1 of n sequence. I will write it as f1 of n wn power 2nk plus summation n is equal to 0 to n by 2 minus 1 x of 2n plus 1 is nothing but f2 of n wn power 2nk into wn power k. So I have represented in other way. We'll call it as equation 2. wn power 2nk, that is wn power 2nk, can be represented as, we know w n is nothing but twiddle factor. Twiddle factor value is e power minus j 2 pi by n into, we have 2nk, 2n into k. So this I will represent it as e power minus j 2 pi divided by, I will take this 2 at the denominator of n by 2 into nk. So this is nothing but, so as here we can see that wn power 2nk, wn is n point DFT. Here we have n by 2, so it is n by 2 point DFT. I can represent it as wn by 2 power nk. So now therefore equation 2 can be written as x of k is equal to summation n is equal to 0 to n by 2 minus 1 f1 of n. So this term is nothing but wn by 2 power nk, wn by 2 power nk plus, I will take wn power k out of the summation, wn power k summation n is equal to 0 to n by 2 minus 1 f2 of n into wn power 2 nk is nothing but wn by 2 power nk. Here the first term is nothing but DFT of f1 of n. So DFT of f1 of n is f1 of k, and f1 of k is n by 2 point DFT, plus we have wn power k, this is DFT of f2 of n, which is nothing but f2 of k, that is x of k. So this is x of k in terms of decimated sequences f1 of k and f2 of k, where f1 of k and f2 of k are 2n by 2 point DFTs. I will call it as equation 3. So also we know that here f1 of k and f2 of k are periodic with period n by 2, because DFT is periodic with period n. Here f1 of k and f2 of k are n by 2 point DFTs. Therefore these are periodic with period n by 2. Therefore f1 of k is also equal to f1 of k plus n by 2. Similarly f2 of k is also equal to f2 of k plus n by 2. So therefore now equation 3 can be written as, so here I will replace x of k by x of k plus n by 2, because x of k is periodic with period n by 2. X of k plus n by 2 is equal to f1 of k plus n by 2 plus, here we have wn power k. N is also periodic, therefore I can write it as wn power k plus n by 2 into f2 of k plus n by 2. So now here we know that wn power k plus n by 2 is equal to wn power k into Wn power n by 2. So here I can represent it as Wn power k into this term I will represent it as e power minus j 2 pi by n into n by 2. So here n will get cancelled and 2 will get cancelled. E power minus j pi is minus 1, which is equal to minus Wn power k. So therefore we can say that Wn power k plus n by 2 is same as minus Wn power k. So therefore now I can represent this equation as x of k plus n by 2 is equal to f1 of k plus n by 2 minus Wn power k plus n by 2 is nothing but minus Wn power k f2 of k plus n by 2. So I will call this as equation 4. So now I will rewrite equation 3. From equation 3 I can write it as x of k is equal to f1 of k plus Wn power k f2 of k. X of k is equal to f1 of k plus Wn power k f2 of k, and similarly from equation 4 I can represent it as x of k plus n by 2 is equal to f1 of k plus n by 2 is nothing but f1 of k only because of periodic plus. So here minus Wn power k minus Wn power k, we have f2 of k plus n by 2 is nothing but f2 of k, f2 of k. So in this case the range of k is less than k is less than or equal to n by 2 minus 1 greater than or equal to 0, whereas range of k in this case is n by 2 less than or equal to n minus 1, because both are n by 2 point DFTs. Now I will call it as equation A and this as equation B. So now I will try to represent equation A and B in terms of signal flow graph, or also known as butterfly diagram. So this is the shape of butterfly diagram. Here these two nodes indicates input nodes and these two nodes indicates output nodes. So here in this equation f1 of k and f2 of k are the inputs, that is f1 of k and f2 of k are the inputs. Those I will write here f1 of k and here it is f2 of k. Here we can see that in equation A x of k is the output, this is x of k, and here it is x of k plus n by 2. So now I will try to represent this equation A. X of k is equal to f1 of k, this is f1 of k signal directly connected to x of k, plus Wn power k into f2 of k. So here I have f2 of k, this f2 of k should be multiplied with Wn power k. So here on this line I will write Wn power k. It indicates that f2 of k will be multiplied with Wn of k, and at this point this signal and this signal will be added up. Therefore x of k will be f1 of k plus f2 of k into Wn power k. Similarly x of k plus n by 2 is nothing but f1 of k. So this line is directly connected here. This is f1 of k minus wn power k f2 of k. So here f2 of k is multiplied with minus wn power k. So on this line I will write minus wn power k. Now I will try to represent this diagram in another way. Okay, I will take the same nodes. These are output nodes. Say these are input nodes. I will take the same inputs, f1 of k, this as f2 of k, this is x of k output, this is x of k plus n by 2. Here I should connect it like this, and here it should be like this. These are the lines. So here we can see that in both the cases wn power k is multiplied with f2 of k. So here I will take the f2 of k. At this point itself I will multiply this with wn power k. So now on this line I am supposed to write 1 because already wn power k I have multiplied with f2 of k here, and on this line it should be multiplied with minus 1. So now this signal flow graph is used for the first stage decimation, that is n point decimation, where input is f1 of k and f2 of k, outputs are x of k, where f1 of k is with respect to even sequences, f2 of k are with respect to odd sequences. So here as I said, the x of n sequence is divided into even sequences, x of 0, x of 2, x of 4 and x of 6. So let these are the even sequences, x of 0, x of 2, x of 4 and this is x of 6. Similarly here we have odd sequences, x of 1, x of 3, x of 5 and x of 7. So this is 8-point DFT, that is first stage decimation. As I said, these are the inputs, f1 of 0, f1 of 1, f1 of 2, f1 of 3 and this is f2 of 0, f2 of 1, f2 of 2, f2 of 3. Here f1 of k, that is f1 of k and f2 of k are n by 2-point DFTs. Therefore k varies from 0 to 3. And these are the outputs, that is x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6, x of 7. Substituting different values of k, that is for k equal to 0, 1, 2 and 3, we can write equation A and B as, substitute k equal to 0 in equation A and B, I can write x of 0 is equal to, here we have f1 of 0 plus wn power 0 f2 of 0. So here we'll assume n is equal to 8. So in place of n I will use 8 so that we can understand easily. Similarly, if we substitute k equal to 0 in this equation, it will be x of n by 2. N is 8, so it is x of 4. That is x of 4 is equal to f1 of 0 minus w8 power 0 f2 of 0. Similarly, for k equal to 1, equation A. Now substitute k equal to 1 in both the equations. So here x of 1 is equal to f1 of 1 plus w8 power 1 f2 of 1. Similarly, in this equation, if we substitute k equal to 1, it will be x of 1 plus 4, that is x of 5. That is x of 5 is equal to f1 of 1 minus w8 power 1 f2 of 1. Similarly, for k equal to 2, it will be x of 2 is equal to f1 of 2 plus w8 power 2 f2 of 2. Similarly, substituting k equal to 2 in this equation, that is 2 plus 4 is 6. X of 6 equal to f1 of 2 minus w8 power 2 f2 of 2. For k equal to 3, we have x of 3 is equal to f1 of 3 plus w8 power 3 f2 of 3. Substituting k equal to 3 in this equation, it gives x of 7 is equal to f1 of 3 minus w8 power 3 f2 of 3. That is, these are first decimation outputs. Now I will draw the signal flow graph after first decimation. Flow graph after first stage decimation. Here there was 8-point DFT block that I have removed with this butterfly diagrams. So here, as per this equation, we have x of 0 is equal to f1 of 0 plus w8 0 f2 of 0. X of 0 is f1 of 0. This signal goes like this. So this is f1 of 0, and here we have w8 power 0. It will be multiplied with f2 of 0, and this signal will move like this. Here these two will be added. This produces x of 0. Similarly, here we have x of 4 is equal to f1 of 0 minus w8 power 0 f2 of 0. That is f1 of 0. This signal comes like this. W, here it will be 1, and on this line it will be minus 1. Similarly, this is x of 1 is f1 of 0 plus w8 power 1. This signal goes here, and similarly for x of 5, this signal, and this will be minus 1, this will be plus 1. Similarly for x2 of 0, it will be 1, and here we can see that it is w8 power 2, and for this line it will be minus 1, that is x of 6. And for x of 3, it is 1, here it will be w8 power 3, and here it will be minus 1. So this is the butterfly diagram. So this is the same butterfly diagram that I have drawn here. Now let's see the second stage decimation, that is 4-point DFT. So now this process of decimation continues. Now we'll do the second stage decimation, where 4-point DFT is decimated into two 2-point DFTs. So here, let the input for this is a of 0 and say a of 1. Input for this is b of 0. That is, 4-point DFT is divided into two 2-point DFTs. So output of first 2-point DFT is say a of 0 and a of 1. Output of second 2-point DFT is say b of 0 and b of 1. Similarly, for this 4-point DFT, again decimated into two 2-point DFTs. That is, this is the output of first 2-point DFT. We'll call it as c of 0, this as c of 1, and these are as d of 0, and this is d of 1. The equations for second stage decimation are as follows. the output f1 of k is equal to, in general, a of k plus w n by 2, because it is n by 2 point DFT, power k b of k. Similarly, f2 of k will be equal to c of k plus wn by 2 power k d of k. So now, like equation A and equation B, where it was n point DFT, now I can write this f1 of k as f1 of k plus n by 4 is equal to a of k minus wn by 2 k b of k. Similarly, for another 4 point DFT, I can write this equation as f2 of k plus n by 4 is equal to c of k plus wn by 2 power k d of k. So here, in all the cases, k will be less than or equal to n by 4 minus 1, greater than or equal to 0. So now I can write second stage outputs for k equal to 0 and 1. So for k equal to 0, this equation can be represented as f1 of 0 is equal to a of 0 plus w4 of 0 b of 0. So here for k equal to 0, we'll assume same n is equal to 8. 8 by 2 is 2. f1 of 2 will be equal to a of 0 plus minus w4 of 0 b of 0. Similarly, for k equal to 1, it will be f1 of 1 is equal to a of 1 plus w4 power 1 b of 1. Here for k equal to 1, we'll get f1 of 3 is equal to a of 1 minus w4 power 1 b of 1. So these are the outputs of first 4 point DFT of second stage decimation. Similarly, with respect to these values, for different values of k, we'll get w4 power 1 d of 1. So now I will show how signal flow graph looks like after second stage decimations. So this is the signal flow graph after second stage decimation. That is, f1 of 0 is the output, which is equal to a of 0 plus w4 power 0 b of 0. So this is f1 of 0, which is equal to a of 0 plus w4 of 0. Here twiddle factor is w4 of 0, which is multiplied with b of 0. w4 of 0, this will be 1. And similarly, we have, now we'll take the corresponding butterfly output, that is f1 of 2. This is done. Now we'll take f1 of 2, because this is the second output of same butterfly. That is, f1 of 2 is equal to a of 0 minus w4 power 0 b of 0. That is, here it is minus 1. This will be the arrow mark. That is, f1 of 2 is a of 0. b of 0 is multiplied with w4 power 0. And similarly, f1 of 1 is a of 1 Here twiddle factor will be W4 power 1 and here it will be minus 1 like this. So here we can also write it as W4 power 0 considered n equal to 8. We can represent all twiddle factor values in terms of 8 as W4 power 0 is same as W8 power 0. Similarly, W4 power 1 is same as W8 power 2. So similarly, here we have F2 of 0, F2 of 1, F2 of 2 and F2 of 3 which will be equal to, so this is 1, this will be minus 1. Here the twiddle factor is same, that is W4 power 0 or W8 power 0. Similarly, this will be minus 1 and this is F2 of 2. So for F2 of 1, this is the signal, that is C of 1, D of 1 multiplied with W4 of 1 or W8 2. This will be signal and here it is minus 1. So these are F2 of 3. So now the decimation is continued until we reach 2-point DFT. So now we have reached 2-point DFT. Now I will try to replace these blocks by signal flow graph. Now here we know that the input here is x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3 and x of 7. So for the first 2-point DFT, the outputs are A of 0 and A of 1. In general, output of first 2-point DFT is represented as A of k is equal to, the inputs for A variable is x of 0 and x of 4. It is x of 0 plus w n by 4 power k x of 4 and x of k is also equal to x of k plus n by 8 is equal to x of 0 minus wn by 4 of k x of 4. So therefore for k equal to 0 we can write A of 0 is equal to x of 0 plus w2 power 0 x of 4. Similarly substituting k equal to 0 in this equation, we'll get A of 1 is equal to x of 0 minus w2 0 x of 4. So similarly, the B for the next 2-point DFT, the outputs are B of 0 and B of 1 and the inputs are x of 2 and x of 6. This can be written as B of 0 is equal to, inputs are 2 and 6, x of 2 plus w20 x of 6. This is B of 1 is equal to x of 2 minus w20 x of 6. So now similarly, the third 2-point DFT outputs are C of 0 and C of 1, inputs are x of 1 and x of 5. We can get a C of 0 is equal to x of 1 plus w20 x of 5 and C of 1 is equal to x of 1 minus w20 x of 5. Similarly, D of 0 is equal to, the inputs are 3 and 7, x of 3 plus w20 x of 7 and D of 1 is x of 3 minus W20 x of 7. Now I will draw the complete signal flow graph of DIT-FFT algorithm. So here A of 0, here it will be signal goes like this. This is 1 and this is minus 1. The twiddle factor value is here W2 power 0, or it can be represented as we have considered n is equal to 8. It may be W8 power 0. So these all are same. And here it is W20, W80. B of 0 is x of 2 and x of 8, 6. Similarly, B of 1 is x of 2. Here it is minus 1. For C of 0, x of 1 and x of 5. For C of 1, it is x of 1 and x of 5. That is minus 1. This is plus 1. This is minus. This is the complete signal flow graph of DIT-FFT algorithm. Thank you for